I'm recording. Okay, I'm not going to use this fancy new webcam because it's, well, I don't know. Maybe, and today I won't try with the non-webcam, the normal camera, the PowerShot, because it's just a pain. It's high resolution, but I have to keep stopping every 30 minutes. So what did I do with my pen? Okay. So today, actually, no new material, because this is just sort of a review of what we've gone through so far, which is actually a lot. Apparently, the faculty is saying I'm going maybe a bit too fast, a bit too hard. So I should really ease off. So I will tone down the midterm a bit. And maybe I actually will answer questions. Admittedly, the first few lectures were terrible. Where I was trying to do it with that notepad where I just had the iPad. Those were really bad. Now, so unfortunately, I haven't had it. Today is also going to be maybe a bit hit or miss because I was watching a friend give her invited talk at a conference from 9 until 10, and then 10:30 I had a meeting with Andrew until a few minutes ago. So I have to remember what I want to do. But it shouldn't be. I have this time. I actually have notes. So why did I do things the order I did them? So the first, I'm going to close that door so you don't hear the traffic. So I wanted people to sort of start the course understanding that problems are surprising things and there are interesting relations between problems. Because I found that before in the fall semester, I left that until the end with NP completeness, and people didn't really get it. And I think it's a key thing in computer science. It's not absolutely a learning requirement of this course, but it's something I feel you should know. So at the beginning, we talked about, actually I'll make this a bit bigger. So we talked about Eulerian cycles and Eulerian paths, which are given a graph. Is it possible, a connected graph, is it possible to start at some vertex and wander around the graph and cross all the edges exactly once and get back to where you started? The graph is Eulerian if you can do that. So this date goes back to like the 1800s. I think it was 1850 something, maybe earlier than that. 1600, I forget, with this bridges of Königsberg problem. And it turns out that it's really easy to tell if a graph is Eulerian because you just count the degrees, and all the degrees have to be even, the graph has to be connected, and all the degrees have to be even. And how do you actually find an Eulerian graph? Well, you just go out and wander around and find a cycle, and you're guaranteed to be able not to get stuck. Because every time you arrive at somewhere, you reduce the degree by 1. So now the degree is odd. So you have at least one outgoing edge, so you can leave. And so the only place you can get stuck is when you get back to where you started. So you do a walk, you get back to where you started. Then maybe you do another walk, you get back to where you started. And so this way you decompose the graph into cycles. And then to glue these into one big cycle. You just pick a cycle, walk around it until you get to some vertex it shares with another cycle, walk around the other cycle, and then finish walking around the first cycle. So it's easy to build an Eulerian cycle, if there is one. On the first assignment, you were supposed to do that to find an Eulerian path, actually. So this is easy, right? And then we saw Hamiltonian cycles. Which is sort of the same thing. Now you're given a graph and you're asked, is it possible to walk around the graph, get back to where you started, and visit each vertex exactly once? And that sounds very similar. I mean, you would think if we can do this, then we should be able to do this. It's almost the same problem, except Euler came up with a solution to this problem quickly, and Hamilton came up with a solution to one instance of this. But in general, hundreds of years later, we still don't know how to do this. We don't have a polynomial time algorithm to tell if a graph has a Hamiltonian cycle. So this is surprising. It's not something we can do this by itself. It's not so surprising. It's not so surprising we can't do this. What is surprising is that we can do one and not the other. The one is super easy, and the other one is really hard. So that's sort of. I wanted to start the course with this sort of surprise. Then you have this problem of three-colorability. So, given a map, can you color it with three colors such that any two regions that share a border are not the same color? So, I mentioned that you can always do this, you can always four-color a map. So to determine whether you can three-color a map, you can view the map as a graph where each region is a vertex, and two regions have an edge if there's an edge between two regions if they share a border. And so can you color a graph, a planar graph? And that sounds quite different, but we'll see after the midterm that you can actually, and it's not a hard reduction, that these two problems sound much closer. But actually, these two problems, if there's a polynomial time solution for one of them, there's a polynomial time solution for the other one. So we started to get into, well, first we explained, we introduced divide and conquer and saw that it can be used for these very hard problems. So we have Nova Scotia. Right. Okay. Very roughly Nova Scotia, with the wrong number of counties and stuff like that. And so to introduce why divide and conquer, sort of just to give an idea for this, if you're trying to count the number of three colorings of Nova Scotia, well, you could brute force it. You could run through all of the 3 to the 18 possibilities. But you can also say, okay, if there are X colorings of the mainland and Y colorings of Cape Breton Island, then there are X times Y colorings of the whole thing. Because Cape Breton Island doesn't touch the mainland, so for every way you can color Cape Breton Island, you can color the mainland all of the ways of coloring the mainland. Okay? So this you can separate this problem into two pieces and deal with them separately. Now, you can't do that as easily for the mainland because it's all connected, but what you can do is choose two counties, say Hansen-Lunenburg or something like that, and say, okay, if I pick, okay, I think this actually goes like this. If I pick these two and I wipe them out, then you've disconnected the mainland. Okay, so you can count the number of ways of coloring the mainland by saying, okay, I consider all the possible ways to color Hansen-Lunenburg, and then for each way to color Hansen-Lunenburg, I count the number of ways to color the north part, I count the number of ways to color the south part. So if this is red and this is green, then I can count this. I can count the number of ways to color here. I can count the number of ways to here, and then again I do the same thing. I multiply. So this is the idea that you can apply divide and conquer even to very hard problems. So we went from this hard problem, and we also saw reductions. For example, we saw that you can reduce not planar three colorability to planar colorability, because planar four colorability you always just say yes, but you can reduce three colorability to four colorability by gluing on an extra vertex. So we got into this idea of reductions. Okay. So this, we start to see divide and conquer and reductions. And we start to see this landscape of problems where one colorability is trivial, two colorability we can do with breadth first traversal. Three colorability we don't know how to do. Four colorability, planar four colorability we do know how to do, and planar five colorability and six colorability and so on. But four colorability in general graphs we don't know how to do. So we start to see that there's this geography, this landscape, this map. And so we start to say this is in polytime, this we don't think is in polytime, this we don't think is in polytime, and we start to see some equivalences. We then saw max sum subarray, and saw how to do that. So we saw how to do max sum subarray in O(n) log n time using divide and conquer. And then we talked about, so remember that was pretty easy. That was just consider the three cases. Either the max sum subarray is on the left, or it's on the right, or it crosses the middle. And if it crosses the middle, then it becomes an easier problem because you just have to find the max sum suffix of the left and the max sum prefix to the right, and you can find a max sum suffix or a max sum prefix just using a for loop. So we then talked about max sum subarray in a circular array. we notice that this is equivalent to this. So this was reduction. You can solve this by solving this, and then turning. If you have a solution of this, you can turn this problem into two instances of this problem. So this is again a reduction. So this is divide and conquer again, and reductions. Okay. So by this point, we should be getting happier with the idea of landscape of problems and divide and conquer and reductions. So in particular, we should be getting used to the idea that if I can reduce A to B, so problem A reduces to B, then if I have a solution for B, then I have a solution for A. So actually, let's not put B, let's just say this, if I have a solution to B, then I have a solution to A. So sort of positive results, upper bounds, go backwards across this arrow. Right? So if you can reduce A to B, then solving B gives you a solution to A. How do you solve A? Well, you take your instance of A, you turn it into an instance of B, you solve that, it gives you a solution to your instance of A. So how do I solve maximum subarray in a circular array? Well, I turn it into some instances of maximum subarray in a normal array, I solve those, and it gives me a solution to my maximum subarray in a circular array. Okay, so then the opposite also holds true. So if A is hard, then B is hard. Okay, assuming that this reduction is fairly easy. So what that means is, if I have proof, or I have evidence, or I believe that, for example, A does not have a polynomial type solution, and I can reduce A to B in polynomial time, then B should also not have a polynomial time solution. So negative results, hardness results flow forward across these arrows. Okay, so you can build up whole networks of these problems where you can have the reduction. It relates A to B, B to C, A to D, whatever. And that way you can say, well, now this stuff is hard because I've proven that one of these things is hard and it reduces the rest of these things. Whereas these are easy because I have a solution to one of these and the other stuff reduces to that. Okay, so positive results go backwards, negative results go forwards. Okay, so we've seen divide and conquer for a really easy problem, and we've also seen divide and conquer for a really difficult problem. What's making that funny noise? It's not my thermos. Okay, can't tell. Can you hear that? Yeah, okay. That was my thermos making some funny squeaky noise. Okay, so we then went into, we saw this Karatsuba's algorithm. and Strassman's algorithm. So remember, Karatsuba's algorithm is for multiplying two really long numbers. And you do this by cutting the numbers in half. And then you have this tricky identity where instead of sort of doing 4 multiplications of these, so you have 1, 2, 3, 4, 5, 6, 7, 8, and 9, 8, 7, 6, 5, 4, 3, 2. Then you cut them in half, and you say, okay, this part is x1, and this part is x0, this part is y1, this part is y0, and then you say, okay, so you have the z2 and z1, z0, and you have this tricky identity where you say, okay, z1, I think, is equal to x1 plus x0 times y1 plus y0 minus z2 minus z0, I think. So you write it, so, and it gives you, you do three multiplications and a bunch of additions and subtractions instead of 4 multiplications, and this gives you a speed up, and the speed up you end up using instead of n squared, which is what you would do with the naive algorithm, you end up using n to the log base 2, 3, I think. So this is a bit surprising because this is multiplication. It's something we've been doing forever. But it took until 1962 for somebody to actually realize that you could do this faster. Oh, we also did Euclid's algorithm in here, I believe, which was sort of the algorithm is really simple. It dates from what, like 300 BC, but it took until 1844 for anybody to actually consider how fast it goes, and it's logarithmic time. Okay. Strassman's algorithm is the same thing, except you're doing matrix multiplication, and you cut each matrix into 4 parts, and then you have that really long and complicated set of, I think, 7 identities, so you do 7 multiplications instead of 8. Okay. So this was really hard with divide and conquer, this was really easy with divide and conquer, this is not so easy, and this is getting really tricky, but these are still polynomial time. Okay. We had the asymptotic notation. And the master theorem. So asymptotic notation is, remember, we want to talk about how fast algorithms are, and we want to ignore the constant factors that can change if we run it on a different computer. And we want to consider only sufficiently large inputs. We don't want to consider, on inputs of size 5, insertion sort is faster than quicksort. Well, who cares? We want to talk about big things, for sufficiently large, for big enough inputs, how do these things behave? And we want to ignore constant coefficients. So we get into this idea of sets. So big O of f of n says, okay, there exists an n0 such that for n larger, there exists an n0 and a c such that for n larger than n0, this is bounded by c times f of n. And then so we're talking about like the running time of an algorithm is in big O of f of n if you can find this n0, if there exists the n0 and the c. We get into big omega, and then if something is in big omega and big theta, then we actually know sort of to within constant factors how it behaves. Somebody mentioned best case and worst case. I said we're not going to talk about best case, then I went and put it on an assignment, so I'm sorry about that. But generally, it's not best case and worst case. It's not that big O is worst case and big omega is best case. It's that big O is an upper bound. It bounds from above. So it says, okay, for sufficiently large n and to within a constant factor, if f of n is in g of n, then g of n bounds f of n from above. If it's in big omega, if f of n is in big omega of g of n, then g of n sort of bounds it from below. It says, okay, it has to be above that. So we got a little omega, little o. So I gave the example of searching in a doubly sorted matrix, where all of the stuff here is ones, and then you have twos on the diagonal, and then you have 4 down here, except one of these might be a 3. And we saw that, well, you can clearly do this if this is n and this is n, you can clearly do this in n squared time. Can you do it in n log n? Yes. Can you do it in O of n time? Yes. But can you do it in better than O of n time? Because it feels like you might be able to. But you can't because, oh, sorry. Right, originally that we said is doubly sorted. This was the example we gave to show that you can do it in better than linear time because you at least here have to look at the diagonal. So remember, people were suggesting we choose the middle point and it knocks out and we recurse, but it doesn't work. And this is the counterexample that shows that no, the time you need for this problem is O of n, because we walk over and find the dividing line between the regions where stuff is less than the target and stuff is bigger than the target. And it takes omega n, because in this case you have to check the diagonal. So this way, the problem isn't theta. Okay. So moving right along. So the master theorem is this sort of plug-and-chug way of solving recurrences that frequently come up with divide and conquer algorithms. So there are the 3 cases: one where the splitting and joining is what dominates it, so it's really hard it's really hard to do the processing at that level. One case is where the work is it splits into so many subproblems, those tend to dominate. And so you can sort of ignore the work at any particular level, and down at the bottom of the recursion tree, there are so many leaves that's what you have to consider. It's the number of leaves. And then there's this other case where it's like, okay, they're sort of balanced, at which point it's generally going to sort of add this logarithmic factor, because you don't just have to count the leaves. You don't just have to count the work at one level. You actually have to look at, well, you have to sum all levels. So there's these 3 cases. It doesn't always work, but it's generally good for what we usually want to do if you're analyzing divide and conquer stuff. So remember this, the big O and big omega. This is big omega, even though it's a word we're talking about worst case stuff. It's not worst case and best case, it's upper bound and lower bound. So we looked at merge sort and quick sort. So merge sort, we just plugged it into the master theorem, and we got that it's merge sort is O of n log n, just out of the master theorem. Quick sort is a bit harder, so we looked at quick select, and we saw we looked at why quick select has linear expected case. So if it divides properly, if you're lucky at each step, then it will run in logarithmic time. And then we did the analysis. So it's easy to see that quick sort is n squared in the worst case, but we went through and did Chernoff bounds to see that it's n log n with high probability. And you don't have to know Chernoff bounds, but the feeling is, remember this idea that if you have the array and you say, okay, well, if I pick the pivot, if this is the array when it's sorted, and you're going to pick the pivot and it'll be somewhat randomly, the chances you picking it in the middle half is a half. In which case you can shrink the you're going to split at least a quarter of the array will go one way, and at most 3/4 will go the other way. And so the recursion works. It's going to work in the tree will have logarithmic levels if you pick it in this middle half, and you can say, well, okay, so if I pick a pivot and it's not in the middle half, so the split is bad, then I can just ignore it and do that again. And what are the chances that I'm going to have to pick a pivot many times? Not very likely. So that's the intuition. So that was the end of divide and conquer. And then we started greedy algorithms. So we did this merging lists. So for merge sort, suppose that something breaks down, and somehow you end up with a bunch of unequal length lists, and you have to merge them. They're sorted, but you have to merge them into one list. And the cost of merging two lists of lengths n1 and n2 is n1 plus n2. What is the optimal strategy for merging the lists? And so the greedy solution is to do sort of either what gives you the most gain or the least pain at each step. So the least pain in this case is to merge the two smallest lists. So if you follow that strategy through, you want to argue if you always merge the two smallest lists until eventually you've merged everything into one, you want to argue that that's optimal. And so we say, well, any merging strategy where you merge sort of at each step you merge two lists is going to be you can represent it as a tree, and it turns out that each of the original lists contributes a cost that is equal to its each element in that list is going to appear in each merge. It's going to contribute to the cost of each merge on the way from that leaf to the root. So we went through this idea that, okay, we can swap two leaves if there's a heavy leaf that's deeper than a light leaf, and we swap them, we're not increasing the cost. and we can swap two leaves at the same level without changing the cost. So therefore, if there were an optimal tree, then we could swap. So we're just considering our next step and trying to prove it's correct. And we say, okay, consider an optimal tree. Now we can swap the two light, the smallest list, down to the bottom level without increasing the cost, and then we can swap them around until they're siblings. And that means that there exists an optimal tree in which we merge the two smallest lists. Okay, so then we get into this inductive argument that, like, okay, well, in that case, before we take any steps, we haven't messed up. Our empty subsolution can be extended to an optimal solution. Suppose that after I steps, there exists an optimal solution S that extends our subsolution. Then after I plus 1 steps, there exists an optimal solution S prime that extends our subsolution after I plus 1 steps. And then by induction on the number of steps, our greedy solution works. Okay, so then we got into Huffman's algorithm, which turned out to be the same problem as merging lists. So constructing an optimal prefix-free code is the same thing about building a binary, given a set of weights, build a binary tree such that the sum over the leaves of their weights and depths is minimized, which is a famous algorithm, famous problem, famous algorithm, but it turns out to be the same as this, and I think this is easier to remember why it works. It's also easier on me because the proof that this is correct is not so intuitive and so it's painful to explain, whereas people actually manage to figure out this algorithm by themselves. So I think it's more intuitive. We also saw the implementations. So normally, how would you implement Huffman's algorithm? Well, if you're given the weights, then you sort of put them in a priority queue, and so you're always taking the two smallest weights at each step. But remembering back when we were talking about sorting, we said, okay, in some cases, for example, if all your numbers are from a small range, then you can sort in constant time, not constant, in linear time. In general, we saw this lower bound on sorting that because if you're doing comparison-based sort, then you're considering a tree that has to have at least n factorial leaves. In which case, so the tree has to have at least log n factorial, which is n log n depth. So there has to be some computation that takes bigger n log n time. But if that's in general, if it's from a small range, then you can sort by just saying, okay, well, I'm going to use memory equal to the size of the range, and then you can just do this by putting things in the right bins. So while normally you would do Huffman's algorithm with a priority queue, you can also do it with Van Leeuwenhoek's algorithm, which assumes that so priority queue which assumes that you sort the weights at the beginning, or you're given the weights and they're sorted, so you put them all in one queue, and you have this other queue, and then the two smallest items will always be at the head of the queues. So you're going to take the two smallest items, add them, and then put them at the back of the second queue. And and so in the lectures we saw this argument of why is this linear time. Okay, so this is O n log n, and this is O of n after sorting. Okay. Then we saw a fractional knapsack with greedy. Okay, so this was when you were filling up your knapsack, you wanted the maximum value, and you could cut the items. So what would you do? Well, you would always take the item with the most density. So the highest profit to weight ratio. And you would just, and you would fill up your, that way, and maybe you have to cut the last item. So we also saw vertex cover, and we saw the proof of this using the same. After 0 steps, we can extend our empty subsolution. Assume that after I steps, we can extend our subsolution optimal solution as blah blah. We saw vertex cover in a tree via greedy. And then we talked about this simple version of knapsack, but binary knapsack, where you either take the thing or you don't. And we said, okay, greedy doesn't work, but it does give you a 2 approximation, where the densities are uniform. So it's binary, but the densities are uniform. And then you would take the biggest thing, and we argued that this will give you, in general, give you an optimal solution, but it will give you a solution that gets at least half as much as the optimal. So then we saw binary knapsack. With uniform density. And then we saw vertex cover in a graph. Which is a hard problem. We do not have a polynomial time algorithm for this, but using this greedy idea, we said, okay, well, we can find a maximal, greedily we can find a maximal matching, where a matching is a set of edges such that they don't have any endpoints. It's maximal if you can't add any more edges to that. We said, okay, if we just take the endpoint, we take, for all of the edges in the matching, we take both their endpoints. Well, each of those edges must be covered by some vertex in any vertex cover. And this way, we're covering all of the edges. If we take both endpoints of all of the edges in the matching, then we're covering all of the edges, because every edge that's not in the matching must touch one of those endpoints, otherwise we could add it to the matching so the matching wouldn't be maximal. And so any vertex cover must cover all of those edges, so it must have at least one of the endpoints of each edge in the matching, and it can't cover, and you can't have one vertex in your cover that's covering 2 edges in the matching, because then it wouldn't be a matching, because those 2 edges would have to share an endpoint. So we did fractional knapsack with greedy, we did vertex cover in a tree with greedy. These 2 were optimal. But then we did a 2 approximation of binary knapsack with uniform density, and we did a 2 approximation of vertex cover in a graph. Okay? Maybe the faculty is right. and I'm making this course a little normally you wouldn't get to approximation algorithms in your first course in algorithms, but the thing is, this is your only course in algorithms. You're not going to see algorithms again unless you take algorithms 2 with Norbert. And looking at the enrollment numbers, most people don't. So, I mean, this is the only chance for most people. Okay, so then we saw minimum spanning trees. Minimum spanning trees. So we saw Kruskal, Prim, and we discussed, so Kruskal is the one where you sort the edges, and then you always take the next cheapest edge, and if it creates a cycle, you throw it away, and if it doesn't create a cycle, then you add it to your minimum spanning forest. Because in general, Kruskal doesn't have, it ends up with a tree, but but before the last step in general, it has a forest. So we prove that this is optimal by doing the same, like after 0 steps, we haven't made any mistakes. Assume that after I steps, we can be extended to an optimal solution, blah, blah. We did prims, which is a bit different, where you always have a tree. So this way you consider the edge incident to your current tree. So remember we said maybe you want to do that. If you have this delicate road paving machine, you can't drive over unpaved roads. So you're going to have to pave the roads. Always you have to select roads to pave that are incident to your current set of paved roads. We talked about the implementations of these. So prims, it's not hard. I mean, you're going to do it with a priority queue, right? So whenever you add an edge, then you're going to look at the edges that are incident to this new vertex that you can reach, and you're going to put them in your priority queue. So that's using a data structure we know, like a heap, to implement a priority queue. So it's pretty easy. But Kruskal's is not so easy because you think, okay, well, how do you, if I take an edge, I want to know, does it create a cycle? In prims, it's easy because I have my vertices that are in my current tree colored blue and everything else is colored red. And so if I take an edge, so until Andrew just talked to me, I would say, of course, you need to know everything. But now the faculty has said, stop being so mean to your students. So, okay, like on the midterm, I mean, this class is distance. So actually, I'm never going. I can't stop you checking the internet or whatever. I mean, there's no way I can actually prevent you looking stuff up, so I'm not going to try. So on the midterm, I'm asking you not to like hire some algorithms grad student to write your answers, but you can check the book and you can, if you don't remember the details, this is not going to be like the fall semester where I actually made people remember this stuff. But I let them have like a page of notes in the final. This semester, as long as you sort of remember how stuff relates and you know where to find the information, then yeah, you can get away with just remembering the broad outline. So Kruskal, you think, okay, with prims, it's easy to check if an edge creates a cycle, because if it creates a cycle, it's between two blue nodes. But, and if it doesn't, it's between a blue node and a red node. But with crustals, that's not so easy because you have this force. So how do you know if an edge is created a cycle? It's too, I mean, yes, you could do a breadth first traversal from one of the endpoints and see if you ever discover the other endpoint, but that would make the algorithm really, really slow. So instead, we discussed union find. What did I just do in the path here? Okay, so we discussed the union find data structure. And I showed you why this idea of merging the smaller tree into the bigger tree, of making the root of the smaller tree a child of the root of the bigger tree. Because if you consider the tree, that this gives you logarithmic query time. Because if you consider the tree, when you walk from a node, every time you take a step, you're doubling the size of the subtree. So that means everything was at logarithmic depth. And then I told you that with path compression, it actually gets a lot faster. Path compression is when, if I'm looking for the representative of some node and I walk up to the root, then I make everything along that path point to the root. Okay, so that's much faster. It's this inverse Ackermann function, which is, you can think of as constant. It's not quite constant, but so you don't get a linear time algorithm, but you get something very, very fast. Then we did knapsack. With VP, with dynamic programming. So we did that easy version where you can take multiple items. This was appetizers, trying to get 1505, exactly 1505 in appetizers from that cartoon. And that was the idea. You build an array and you fill in the array's answer. You can answer the big problem if you already know the solutions to all the subproblems. So it's a bit like recursion, but it's faster because you keep notes of, you don't have to do the solve the same subproblem over and over again because you already have the answer stored in the array. So you can think of it as you have this friendly, weak-willed professor who you say, Prof, I don't know how to answer this, and the prof says, well, I'm not going to tell you the whole answer, but you can ask me about any problem of this kind, which is smaller. So we did this, and it's recorded. Then, oh right, we talked about factoring. Because with dynamic programming, it seemed like we got a polynomial time algorithm for knapsack. And that's because it seemed like solving that appetizers problem took linear time. We talked about, well, factoring is thought to be a hard problem. Lots of crypto systems are based on factoring. But we found a trivial algorithm for factoring just a for loop. It's like for I equals 1 to n, does I divide n? It's like, okay, we can find all the factors of n in linear time. Why doesn't that break all these crypto systems? And we discussed about the size of the input. So the actual number of bits or digits I need to represent the number is not n. It's not proportional to the input. It's proportional to the log of the size. It's not proportional to n. It's proportional to log n. So actually, yes. Knapsack, you can do knapsack in polynomial time, polynomial in the size of the knapsack, but it's not polynomial in the number of bits needed to represent the problem. Some problems, so knapsack becomes easy if you write all the numbers in unary. Some problems don't. We'll see this again when we get to NP completeness. And then we did max sum subarray. Okay, max some subarray via dynamic programming. Can you see this down here? That's okay. Can you see knapsack? This part of the board is off limits. So I have to say, like, I'm going sort of too fast. This is a lot of material. And normally I would be happy, just a little bit more material, and I would be happy covering if this took almost all of the course. I mean, we still have to do like a week, maybe 2 weeks on NP completeness, and a week on graph algorithms and stuff. But in the fall semester, I didn't get all of this in. I did some other stuff instead of some of this. But this was nearly all the material in the whole fall semester. I went much slower because I kept stopping and pointing at people and saying, okay, what do you think the answer is? And people kept asking me questions, mostly Sarah. So it was, I mean, I got slowed down in a good way. People wanted to know things, there was interaction. Now I don't have only 1, 2, 3, 4, I think 16 students here now. And nobody's really asking me anything. So I'm just sort of going full speed, which is probably too fast. I will try to, yeah, the like 16 people who are here are learning stuff. The other like 90 are I hope watching the video. I really hope watching the videos afterwards. Okay, so we saw max sum subarray via DP, and this was in linear time. So I want to go back to that idea of the reductions, which I just erased, about the max sum subarray and max sum subarray in a circular array. So this means just getting a solution. What does that mean for max sum subarray in a circular array? It means that we can also do max sum subarray in a circular array. This implies we can also do this in linear time. So that's the power of reductions. If you solve, so if you could, later after the midterm, we'll see, if you could solve one of these problems, if you could solve 3-colorability in polynomial time, you would solve Hamiltonian cycle in polynomial time. Bang, it's like you don't actually really have to do any work, it just would happen. It would. So we discussed, this is why people in database, if somebody solved 3-colorability in polynomial time, people in databases would be excited. People in AI would be super excited. People in computational medicine, people in, basically lots of people, cryptographers would be very upset because cryptography would essentially end. But databases, you could then take this polynomial time solution for 3-colorability, and there is a chain of reductions. So you can reduce this database problem. So I have that book over there, the Gary and Johnson, that has a load of database problems, and there's this chain that says I can reduce this to this, 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 I can reduce this to planar 3-colorability. You can reduce 3-colorability to planar 3-colorability. So if I can solve, and all of these reductions take polynomial time, there's a polynomial length chain of them. It's actually constant. So if I could solve this, if I could solve three-colorability, I would get polynomial time solutions to problems in databases. And the databases people would be super happy. They'd be really surprised, but they'd be happy. Okay, so we saw a very small example of that happening here. We sped up the algorithm for this, and we got a faster algorithm for this problem for free. So then we saw that ladder problem, where I said, okay, how do you get from the top left to the bottom right? How many ladders can you cross? What is the maximum number? And you said, okay, well, that looks fairly easy if you know how many points you can get crossing ladders here into here into here, then you can work out this how many you can get crossing here, and you have the two quick cases where you either didn't have a ladder here or you did. Okay, remember? And so there was this ladder problem via dynamic programming. And then I showed you that this is actually equivalent to longest common subsequence. So that was the problem where you got a point every time you crossed a ladder, one of these red arrows. And then we said, well, okay, then we just change it around a little bit and say, okay, well, instead of getting a point for crossing the red arrow, you get to cross the red arrow for free. And otherwise, each blue arrow costs you 1. And so how can you get from the top left to the bottom right? Spending as little as possible. And that changes the recurrence, but not a lot, and that's edit distance. And we saw these are these you can do in quadratic time. So if you have a length n string and an s and a length n string s t, then you can find the longest common subsequence of s and t. Remember, a subsequence doesn't have to be consecutive. Or the edit distance between s and t in O of n squared time. But then I was saying that we use this in computational genomics for comparing, for aligning genomes, for example, and there it would, like, the genome is 3 billion characters. You don't want to do this in quadratic with 3 billion. But I told you about this banded dynamic programming. I could have just written BP. Banded means that if I give you an upper bound and I say, I only care about what the edit distance is if it's at most this k, then you know if this is your dynamic programming matrix for the edit distance, if you're looking at some cell down here that's way off the diagonal, then you're looking at the edit distance between a short string and a long string. So this is going to be at least the distance off the difference in the length of the string. So it's going to be the distance off the diagonal. So if I told you that, so this can't, if this is a big distance, much bigger than k, you don't have to look here. You only have to fill in sort of this stuff that's a distance k from the diagonal. Oh yeah, we also saw how to do edit distance in linear space instead of quadratic space. So this is how you can get an O of n k time solution for banded dynamic programming, which is important in a lot of practical things, like computational genomics, which is sort of what I do. And I just lost my train of thought. computational genres, we had advanced dynamic programming. Okay, couldn't have been too important. Okay, all right, and then we did optimal binary search trees. So this is, I showed you if you have, oh, I lost somebody. Oh, sorry. Optimal binary search trees, if you're given probabilities over the keys, and you want to build a binary search tree such that the expected depth is minimized. So this is a bit like Huffman, but in Huffman you're allowed to change the order and you only care about the leaves. Here it has to be a binary search tree. So the idea is here if you want to say, okay, well, suppose I want to pick which key is going to be the root. Well, you can ask your friendly professor about the expected depth of any binary search tree that has fewer than n keys in it. So you just run through all the possible choices of the root, and so if you've got, if you want the root to be j, then you say, okay, you ask your friendly professor about the cost from I to j minus 1. What is the best way to, if you've decided you want the root to be j, what is the best way to build this subtree? What is the best way to build this subtree? And then you can work out the cost of this. So you just have a for loop and you run through all the possibilities of those, and see which one gives you, which is the best choice of the root j. So this gives you an O(n) cubed time, and then I told you that Knuth managed to speed this up with the observation that if you add something on the right of an optimal binary search tree, then so if you have a binary search tree, optimal binary search tree, and you add something to the right, then the best choice of root cannot move left, and vice versa. If you add something on the left, then the best choice of root cannot move right. And so I showed you this this telescoping sum where he managed to speed this up. I didn't prove that. You don't have to know why that's true, but you can, if you do this trick with the root, then you can get this in O(n) squared. Okay, and then we saw the longest increasing substance. So remember, this is, you're given a sequence, you're given a string of numbers, you're asked to find the longest increasing subsequence. So what you do is you try to fill in this array. So if you're given, what was it? I called them red and blue, but I can't remember which one was red and which one was blue. You want to have this auxiliary array such that I is the length of the longest increasing subsequence ending at, what was the other array called? It was blue. Okay, so this was red. The input was blue, ending at bi. So at first we solved this by saying, okay, well, the AI would be 1 plus the length of 1 plus the maximum of yeah, Ri equals 1 plus max Rj such that Bj, okay, such that J is less than I, Bj is less than Bi. So it has to be something to your left. So you're saying, okay, I'm going to look for the longest length I can achieve with something that ends at a number to my left, and it has to be, the number where it ends has to be smaller than the number I'm at now. So we implemented this conceptually on the whiteboard with 4 loops, and we got O(n) squared with loops, with nested loops. And then we said, okay, if we could somehow just ask what is in the stuff before us, what is the biggest number that is less than, what is the biggest number associated with a B value that's smaller than our current B value. And we said, okay, if we had a data structure that would let us ask queries like this and it would answer quickly, then we could do this algorithm faster. And they said, okay, well, so we need something called the dynamic range max data structure. And we saw how to implement that by augmenting an ADL tree. So actually there is, so I should say, okay, I'll just, so remember we saw how to augment we said if we have a binary search tree, we can, if you give me a value, I can cut it. If it has logarithmic height, I can cut it into the part of the tree that values keys less than that, less than or equal, and the part that has values more. So this has if this has logarithmic height, then I actually get a logarithmic number of nodes and subtrees, where each of single nodes and subtrees by looking down this path that sort of divides the tree. So how do I turn this into a dynamic? So if this is an ABL tree, it's always got logarithmic height. How do I turn this into a dynamic range max data structure? Well, each node stores its key is its D value, and it also stores the length of the longest subsequence that ends at that B value, and it also stores, additionally, it stores the maximum length in its subtree. So I can ask, what is the biggest length of ending at any B value that is at most 5 or something like that. And I can walk down in logarithmic time for each subtree that only contains things that are less than 5. That are less than 5. I just check the max that's stored at the root, and at the individual nodes, I check the length of the thing that ends at that key. So this gives us O of n log n. Also, we have the option if somebody says, give us back the maximum that is in some range, then you can do that. So this is kind of important because there is a solution on LeetCode that gets you an order n log n time algorithm for longest increasing subsequence just using binary search in an array. The downside to that is it won't do this range thing. So in the notes for the fall semester, on one of the assignments, I taught them this algorithm, longest increasing subsequence, and then I asked them to solve longest slowly increasing subsequence, where each number in the subsequence can't increase by more than, I forget, like 10% or something like that. So you can go from 9 to 11, you can have 9, 11, but you can't have 9, 13, because it's increasing, but 13 is too much bigger than 9. So you can do this with this kind of range trick where you say, okay, I'm looking at my next number. Either do the scribe notes, you can do both, and I'll take the best mark. I think because of what Andrew just told me, I may end up making the midterm a bit easier than I was going to. I'll tone it down a bit. I don't know whether it would be easier to get a better mark on the midterm or on the scribe notes. So you cannot do, or at least I don't see how to do, this longest slowly increasing subsequence problem using this arrays trick that's on LeetCode. It's also on Wikipedia. The other downside, I have 1 minute, the other downside of that algorithm that's on LeetCode and Wikipedia is the explanation on LeetCode is terrible. I think that solution was posted by somebody who got the code from someone else and didn't understand how it works. The description on Wikipedia is a bit better, but still not great. So, whereas if you watch the lecture on doing this with an augmented ADL tree, then I hope you will actually understand the solution. And understanding solutions is good, not just because understanding in general is good, but because that way you can actually document it and get the points you're documenting, because otherwise, like I would, the solution on LeetCode, the code works, the solution is very neat, but the documentation is abysmal. So it's not going to get good marks, and possibly so if somebody turned in something like that to me, I would be in a difficult situation because that seems to be an academic integrity offense because they're submitting something that's not theirs. So I've never had to deal with something like that, and I hope I never have to. But I'm also not supposed to let it go. So in general, people, even if they get answers from somewhere else, they should understand them. So I think I'm out of time. Are there questions? And that, yeah, that was up to the last thing, the thing we did in the last class. It's a lot. It's really, really a lot. I don't know. I need to go to having the TAs sit in the lecture and ask me questions or something to slow me down. But it does mean that the second half of the semester should be really light. Okay, so there are no questions. Can you clarify the assignment Q1B? What do you mean by reuse? What's Q1? What's 1B? Just a sec. I don't know what 1B is. The max sum question. Oh, okay. Oh, that's just Yeah, now I remember. Assignment 3. Oh, so this is this stuff, I think. Reuse your code in a fast solution max up. Yeah, okay. So this is just, I forget if I asked a question about this on the first assignment, but so you, on the first assignment, you were supposed to, on the first assignment, solve max sum subarray with divide and conquer, and then you were supposed to solve max sum subarray in a circular array by reducing it to max sum subarray. That was on first assignment, I think. Maybe? Okay, so this is just to sort of drive home this point that if you can do this via dynamic programming, you have a reduction from this to this that works in linear time. So you also get a solution to this that works in linear time. You don't have to go out and design a new dynamic program for this. You just have to, I mean, we discussed that if you have a circular array, so if this is the max sum subarray, so you have code, you have a dynamic programming solution to max sum subarray. If this is a circular array, and the max sum subarray is in the middle, then you just call your code and it will find it. So the tricky bit is when it's like this, right? So this instance, it's circular, but you just run your solution for max sum array. Here, if this is the max sum subarray, where did the red go? Then this is the nice observation which I missed in the fall that the students got. This is the min sum subarray. So you can take this, multiply everything by -1. So this is max this is max sum subarray. This is min sum subarray. So you can take this, I run out of space, multiply everything by -1, which takes linear time. And now you get, so this, you multiply everything times -1. Here, that's going to make this red thing then becomes max sum subarray. Right? So this, you can find the sum in here because you find the sum here, you times it by -1, it gives you the sum in here, and then the sum of everything in the array, you subtract this, and it gives you the sum in this. So it's the same reduction from the first assignment. I'm just trying to really drive home the fact that when we sped this up, we sped this up. Because remember I was saying that, so max sum subarray in a circular array reduces to max sum subarray. This reduction takes linear time, and actually you can also go backwards. in linear time. So if we get a linear solution to either of these, we get a linear solution with the other one. So this is just a little example of how speeding up one problem can speed up problems that reduce to it. It's not supposed to be a really hard question. Okay, good. So somebody will get the answer to that. Knapsack, appetizer problem. Are these really the same problem? With appetizer, yes, it does. The thing is this on the assignment? It's either on the assignment or it's... Yes, it is on the assignment. Oh, okay, good. Yeah, Andrew's right. This is way too hard. Oh man. Okay, so the thing is, you don't have to implement your item. Yeah, so this is sort of more, this is the standard form of knapsack. So the trick is, I started with that appetizer one, first because I had a cool cartoon for it. And secondly, because it is easy. It's one-dimensional. But if you're only allowed to use each item once, then you can do it, but it becomes two-dimensional. So the standard solution is what you're going to do, order the items. Any order. So how many items did I say there are? Capacity M and a set N. Okay, so let's say this is the capacity. Okay, let's put 0M. And this is the items from 1 to N. Okay. So now, what you want, I is the row, or I is now going to be here, okay? Ij, this is going to be I, and this is going to be j. It's going to be like x, y, okay? So now you want, and this is all array A. I think this is in the book. Or maybe I want this, yeah, it doesn't matter. Okay. Is true if we can do I want to, if we can get, oh, sorry, not true. Sorry, not true. Is max profit can get from a subset of first I items with weight J. Ah, there's like nobody. Oh, okay, like 5 people here. So Aij is the max profit we can get from a subset of the first I items with weight J. So this way, if we have all of these, how do we then get I plus 1? So if we filled in all of the values here, how do we fill in the values here? And there are 2 ways. You either say, okay, either we take the I plus first item or we don't. I think it's in the book. This is actually the standard definition of knapsack. So it should be easy to find. It's not so different from what we did, but okay. So I think I have to end. Okay. Cheers.